So population genetics is the study of allele frequencies within a population and how it changes over time. So this is linked to evolution, which of course relies on natural selection, genetic drift, gene flow, as well as mutations, all leading to changes in allele frequency. And so we can study this using population genetics. So first of all, what actually is a population? So a population is an interbreeding group of individuals which belong to the same species and they live in the same geographical area, okay? So think of a group of individuals which are all reproducing with each other. So that is a population. So we can study how the allele frequency changes within a population. So in a population, the gene pool refers to the complete set of alleles that is available in this population. So the complete set of all alleles for a gene in a population. Whereas allele frequency refers to the fraction of the genes with that particular allele. Okay, so let's say for a particular gene we have 3 different alleles, allele A, B, and C. That represents our gene pool for that particular gene. And if we wanted to look at the allele frequency, maybe we've got 20% of the population has got the A allele, 20% has got the B allele, and maybe 60% has got the C allele. So that would be the allele frequency. Okay, so the Hardy-Weinberg Equilibrium is something that was established by scientists with the last names Hardy and Weinberg. And they have this formula that we can use, which allows us to study genetic diversity in the absence of evolution. So basically they ask the question, what would happen to a single trait or a single gene encoded by 2 different alleles in the absence of evolution? Okay, so if there's no natural selection, if there's no mutations, if there's no competition, there's no evolution happening, then how is the allele frequency going to change over time? Okay, so Hardy and Weinberg proposed a model to solve this problem. So in order to use this model, or in order for a population to be in Hardy-Weinberg equilibrium, the population must have these characteristics. Okay, so in order to be in Hardy-Weinberg equilibrium, the population is not evolving. So for a population to be not evolving, we need to have no mutations, so no new alleles being added to the population. No alleles being added through immigration or genetic drift, gene flow. Okay, so no migration into the population, no genetic drift. Okay, so no change in allele frequency due to random chance. There's no natural selection, so no particular trait is being selected for in that environment. And there's no sexual selection, so mating is completely random. So if these 5 criteria are met, that means that evolution will not be occurring, and then the population will be in Hardy-Weinberg equilibrium. So the Hardy-Weinberg equilibrium states that the population allele frequencies will not change over time if the conditions above are true. Okay, so remember, evolution is a change in allele frequencies. If there's no evolution, then there's no change in allele frequencies. So your allele frequencies are going to stay the same if these 5 criteria are met. So the Hardy-Weinberg equilibrium is a couple of different formula which allow us to relate allele and genotype frequencies in a population. So let's take a look at the Hardy-Weinberg equilibrium. So first, using this kind of diagram here to illustrate it a little bit. So in this population of bugs, you can see we've got 2 different alleles. We have the big A allele. So we have a big A allele, which gives us green bugs. And we have a little a allele, which gives us brown bugs. Okay? And so we have 2 different alleles, green and brown. And remember that these organisms are going to be diploid. So they have 2 copies of this gene. So the possible genotypes that you can have here would be big A, which would give you a green bug, big A, also giving you a green bug, and little a, which gives you a brown bug. So from our population here, okay, we can determine our genotype frequency in the population. So let's start with determining our genotype frequency here. So genotype frequency. So you can see our total population here is given at the top. We have 1,000 individuals in this population. And you can see that 360 of these 1,000 individuals has the big A genotype. Okay, so for the big A genotype, we have 360 individuals out of 1,000, which gives us a genotype frequency of 0.36, okay, which is shown right here. For the heterozygous genotype, so big A, we have 480 out of 1,000, and so that gives us a genotype frequency of 0.48, which they've given us here as well. And for little a, we've got 160 individuals with that genotype out of 1,000, and that gives us a genotype frequency of 0.16. So in a population, all of the genotype frequencies, okay, the 3 genotype frequencies, are always going to add up to 1. So it adds up to 1. So this big A genotype frequency is given by p squared. The big A phenotype is given by 2pq, and little a is p squared. And so this brings us to one formula that we have in the Hardy-Weinberg equilibrium. P squared plus 2pq plus q squared is all going to add up to 1. So that is our first formula there. Okay, so that's for our genotype frequency. So now let's look at our allele frequency over here. So over here, let's calculate our allele frequencies. Okay, so for the big A allele, we know that we have 360 of these guys, the big A genotype. So we've got 360, which each have 2 big A alleles. So we have 360 individuals, each with 2 big A's. We also have these 480 individuals right here, which have just 1 big A. So plus these 480 individuals here. Out of a total of 1,000 individuals, and remember that these 1,000 individuals all have 2 alleles. Okay, so in our population, we have 1,000 individuals, but each one has got 2 alleles. So that means we multiply our total amount by 2. Okay, so if you calculate that, that would give you a frequency of 0.6. Okay, so just to make sure we've got that down, we had our 360 individuals, which had big A genotype. Okay, so they each had 2 big A's. And we had 480 individuals that had big A. So they all had just 1 big A. Out of a total of 2,000 alleles that we have in this population. So 1,000 individuals gives us 2,000 alleles total. Okay, so for our little a, let's calculate that. So you can see here we have 160 individuals which have the little a genotype. So 160 individuals which each have 2 little a's, plus our 480 individuals which each have 1 little a, divided by our 1,000 individuals which each have 2 alleles. so 2,000 alleles in our population. And that gives us an allele frequency of 0.4. So what you can see is that our allele frequencies here also add up to 1. And our big A allele is given by P, and our little a allele is given by Q. And so that gives us our second formula in the Hardy-Weinberg equilibrium, which is P plus Q is equal to 1. Okay, so these are the two formula that we need to keep in mind for this Hardy-Weinberg equilibrium here. And it kind of makes sense if you look and you do a Punnett Square here using our allele frequencies. Okay, so this is how we kind of derive this first formula over here. So our big A allele here, our big A allele, remember, is given by P. And the allele frequency we calculated for P is 0.6. Okay, and then our little a allele, which is given by Q, we calculated to be 0.4. Okay, so for our mother and our father, we have the same allele frequencies. And so if we were to do our Punnett Square here, you could see in this first square, it would be P times P, giving us P squared, which equals 0.36. So here in this second box, we're looking at our Q and our P right here. So this, I think, is something wrong with the figure. This should actually say PQ here. Okay, and then down here we have another one where we are looking at both our P and our Q. So we have another PQ right here. And so that gives us 2PQ. And then here we have our Q squared. Right? So if you look at this square, you can see that you end up with a P squared, you end up with 2 PQs, and you end up with a Q squared. And all of these are going to add up to 1. Okay, so that's where we got that formula on the left. Okay, so that is how we can calculate our genotype frequencies and our allele frequencies. So again, the two formulas that we have here are our P squared plus 2PQ plus Q squared. These are our genotype frequencies. Okay, so our P squared, our Q squared, and our 2PQ are the genotype frequencies. And then for the allele frequencies, P plus Q is equal to 1. And so P is going to be the dominant allele, whereas Q is the recessive allele. Okay, so how do we test whether a population is in Hardy-Weinberg equilibrium, which is basically testing whether or not the population is evolving? So there are 4 steps to follow when you encounter a question like this. The first step is to calculate the allele frequencies, P and Q. The second step is to calculate the expected genotype frequencies based on those allele frequencies. So our P squared, our 2PQ, and our Q squared. Then we are going to calculate what we would expect under Hardy-Weinberg equilibrium, and then compare the observed with the expected. So in the next couple videos, we'll do an example where we go through practicing these 4 steps. So this question says we have 100 pea plants with the following genotypes. So we've got 60 that have the big A genotype, 20 have big A, and 20 have little a. Is the population in Hardy-Weinberg equilibrium? Okay, so we know that for our big A, we have 60 out of 100 individuals that have that genotype, so that genotype frequency is 0.6. Big A, we have got 20 out of 100, and so that gives us 0.2. And little a, again, 20 out of 100, so 0.2. So the first step that we need to do here is calculate the allele frequencies in this population. So for our big A allele, we have got 60 individuals right here who all have 2 big A's, plus 20 individuals right here who each have 1 big A, divided by a total population of 100, And each of these 100 individuals have 2 alleles total. And so that should give us an allele frequency of 0.7. So now let's calculate the allele frequency for little a. Okay, and so for little a, we have 20 individuals right here who each have 2 little a's, plus the 20 individuals who each have 1 little a, divided by our total population times 2. So that should give us 0.3. Now, one check before we move on to the next step is that these two things add up to 1. Okay, so now that we've calculated our allele frequencies, the next step is to determine the genotype frequencies that would result when this population reproduces. So here we're calculating the expected genotype frequencies. Okay, so next we're going to calculate the expected genotype frequencies of the next generation. Okay, so for our genotype frequencies, we're looking for our p squared, which remember is our big A genotype, okay? And we already calculated our p, which is right here, and this is our q right here, okay? So p squared is given by 0.7 squared, which equals 0.49. Our q squared, which is the little a genotype, is 0.3 squared, which equals 0.09. And then finally our 2pq, which gives us our big A, little a genotype frequency. So 2 times p, which was 0.7, times q, which was 0.3, and that gives us 0.42. So again, before we move on, we want to check to see that all of these add up to 1. So make sure they add to 1, and if you put that in your calculator, you see that they do. Okay, so we calculated our allele frequencies and we calculated our expected genotype frequencies for this population in the next generation. So now we have to compare the expected genotype frequencies with the observed genotype frequencies that was given in the question here. Okay, so let's make a little table here to compare our genotype frequencies, okay, that we expected, so expected, and what we actually observe. Okay, so for our 3 genotype frequencies, okay, so big A, little a, and little a. So we would expect in this population to see genotype frequencies of 0.49, 0.42, and 0.09. And what we actually see in this population is 0.6, 0.2, and 0.2. So you can see that the expected does not match the observed. And what you can also see is that our allele frequency here changed over time. And so that means that this population is not in Hardy-Weinberg equilibrium, which means that the population is evolving. And so that means that at least one of those 5 criteria to be in the Hardy-Weinberg equilibrium is not met. There's something that is causing the allele frequencies in this population to change over time.